Uh, Hello, another video. Sorry, my dogs are fighting. Yeah, I could restart the video, but instead, let's talk about logarithms. So, what is a logarithm? I don't know. Have you taken chemistry? In which case, maybe you already know the answer is still, I don't know what a logarithm is. So to figure out what a logarithm is, we have to think about the one thing we haven't done with exponential functions yet, and that is invert them. If I have something like this, I say, well, ew, why is it that pen? 2 to the power of something equals 32. Well, I happen to know that this is 2 to the power of 5, so I know that x equals 5. But that's just me using logic. I don't really have an algebraic method to do this. And what if I had this exponential function, right? Y equals 2x, and I wanted to find the inverse. Well, the inverse of that would be replacing our x's with our y's. In either case, in here I can guess / logic my way through. And here, well, what am I going to do? I don't have a way to actually calculate this by performing an operation to sort of isolate that exponent. So we're going to need something else. Let's start by looking at what a graph of this would look like. So 2 to the power of x, let's graph that first. So we'll do a table of values here, -3, -2, -1, 0, 1, 2, 3. So that's going to be 1/8, 1/4, 1/2. Anything to the power of 0 is 1, and then we go 2, 4, 8. And that's that nice pattern, kind of our reciprocal versus our log, or not our log, our power. Nice. On our asymptote side, I'm just going to draw the asymptote. I'll draw through the point, right? And then 1, 2, 2, 4, 3, 8. Close enough, right? Yeah, off by only 1. We get this nice point, 0, 1. We get the point at 1, 2, because that's like 1b, like we talked about before. But let's do a inversion of this. So in an inversion of this, what we're going to have is, well, x equals 2y. So we're going to have y equals something. We don't really know the alternative for that now. But what we can write is our points. So I know at the point 1/8, I'm going to have a value of -3. At the point 1/4, I'm going to have a value of -2. At the point 1/2, I'm going to have a value of -1. And then at the point 1, I'm going to have a value of 0. So that's a really good point. Let's draw that one out. Point 2, 1, we're going to have a point at 4, 2, and a point at 8, 3. So let's draw those, just because I know, like here I've got it in the table, here I've kind of separated it out. So let's draw those. 2, 1 is a point, 4, 2, 8, 3. And this point here, we see it as, all right, as we get smaller and smaller, we're getting more and more negative. And so that's going to look kind of like an asymptote, because it is an asymptote. And that's going to swish on through here, through all of our points. And that was actually pretty good until that part. And here you'll notice, like, well, this kind of makes sense. If we draw this line, y equals x, that goes right through here. This does look like it's just reflected about that line. And that's because it is. So we did it right. Woohoo! And we get this looking funny looking function. And the way we write this is saying, well, isolate that. I'm going to do something called a logarithm, where I'm going to have this x value be able to be put in that will give me the y value, the output. And that's really, really cool, because now I've got a function where an operation called a logarithm can take this x, whatever my number is, and tell me what the exponent on our base had to be to get that value. So this is a tool that lets us find out what exponents are. Ooh, and that's a really powerful tool. So here's how it works. If I have y equals bx, the inverse of that is x. Ooh, I don't know why my marker didn't do that. X equals b to the y. And I can convert this into a logarithm by writing y equals log bx. And so let's sort of break this down. This is sort of the two ways of seeing something, right? So As an exponential, we'd write it x equals b to the power of y. And in the logarithmic form, we write y equals log bx. So if I wanted to write this in logarithmic form, I wouldn't find y. I already know what y is, but I could write it like this. X is equal to log b of y. Okay, so there's an exponential form and a logarithmic form for any one of these statements. So these two are connected, and these two are connected, and they're inverses of each other. So let's dissect a little bit our actual terminology here. So if I have a statement like this, y equals log base bx, the value of the y, or sorry, the letter y stands for our value. So this is our value. And essentially, it's like telling you what the value of the exponent is. So this y is going to tell us what the exponent is. All right, the next thing is our base, and base is the same for here, right? Our base of our exponent is going to be the base of our log. So they're equivalent, right? Whatever the base was for the experiment, or not the experiment, the exponent is the same for the log. And then if we've got, I don't know, let's use teal. If we've got a base of b equaling 0, that's not going to work. You can't have anything like power 0 is not really helpful. I can't calculate anything. The last part is this x, which is saying, okay, what is our exponent equal to? What is our power equal to? That's what we're going to be analyzing. So we're kind of performing this opposite operation onto x. And so we call it now our argument. So that's the term for x. You cannot use a negative argument. It's not going to work. And the reason for this is just how it's calculated. And remember, a graph here, we can't put in a negative x value because our asymptote here is at 0. So you don't have anything to the left of 0. You don't have anything negative. Here's kind of our key statement to remember. You know, if we've got y equals log bx, it's equivalent to x equals b to the power of y. And some other important notes here are that we've got logarithms are sort of a default case for them. If you have like on a calculator where it just says log, it'll be in base 10. And there's another number we've got, which is E, and this is Euler's number, E-U-L-E-R-S, Euler's. And it's a special number that we'll talk about in future math classes. But for right now, just know that it's such an important number for later on that if we were doing a logarithm with a base of E, it actually gets its own name, a natural log. And we represent that with Ln. Just in case you're curious what E is where I have sort of our interest formula. So it's 1 plus 1 over n to the power of n, where n is approaching infinity. So obviously, if n is infinity, you kind of, it doesn't really work. But as it approaches infinity, so it's not conceptual, it's actually infinity, this number approaches a value of like 2.718. So it's 2.72-ish. And that number ends up being really, really important for further applications in math. For right now, you just need to recognize when I say ln, I really mean log base E. Okay, so let's see how we could write these in different forms. This is kind of our reminder from before. Well, I take my exponent and that becomes my value. And on the other side of my equality, I've got log in base B. It's the same base as the base of the exponent. And our argument now is whatever the other side of my equality was for the exponent. And so that's converting it. Let's do that again over here. All right, so we know that this is kind of backwards now. So our argument becomes sort of the value on the one side. And then our base is the base of our exponent. And our value over here is the actual exponent. So we get 3 to the power of 3 equals 27. Yeah, it does. How about this one? All right. Well, we've got -3. That's sort of our value here, right? Is equal to log 2 of 1/8. Awesome. One more here. We've got to the power of 5 is equal to 2x plus 4. Nice, easy peasy squeezy lemons. Let's take another look at a couple other ideas like with graphs. If I've graphed this 1/2 of, or 1/2 to the power of x, if I want to graph the reciprocal of this, I'm going to just pick a couple points. So I'm going to pick this point. So we've got 0, 1. Well, that'll become 1, 0. Okay, and actually I should erase this. It's going to get a little confusing. And this looks like it's going to be forming sort of an asymptote here. So let's focus on the other side first. I've got -1, 2, so that's going to be 2, -1. I've got -2, 4, so that becomes 4, -2. And I kind of recognize this point here as well. So if this point is flipping here and this inverse, well, I know I'm going to get this sort of 1 1/2, so it should be 1/2 and 1, so somewhere like up here. And then I'll get that asymptote along the line. And ooh, close enough. That sort of makes sense for us, right? We know that our logarithms can't be negative. And so the logarithms function here still has that asymptote at x equals 0. So perfect, there we go, we got one. Let's look at another sort of question you might see. And this is sort of getting into the meat of logarithms here. We're going to be doing this stuff a ton. What we're going to want to do is be able to logic our way through some of the ways to do math with this. And one of the tools we have is that if I know a logarithm and an exponential, they're kind of the same, they're equivalent ideas, then what I can do is I can rewrite logarithms in exponential form. That should help me solve. So let's do that. Okay, our base is 2. Our value of our exponential is 2. And our argument is just what's on the other side. So rewriting this becomes a really simple math equation, right? So I've got 2 to the power of 2 is 4 equals y over 6. I'm going to multiply both sides by 6, and I end up with y equals 24. Sick. How about over here? Well, let's do the same thing. 3 cubed should be equal to 36y. All right, well, 3 cubed is 27 equals 36y. And then if I divide 36 over, that gives me 27 over 36, which actually is equivalent to 3 over 4. Kind of neat. Now, we know that logarithm functions are functions, so we can do transformations to them as well. So here's sort of our basic form of a logarithm. And when we're dealing with logarithms, we kind of like using a couple specific points. So our x-intercept, when our y value is 0, it's because our x value is 1. So this is an important point, that 1, 0. And that's the opposite of our 0, 1. We also have this x equals 0 vertical asymptote. That's important. And that kind of guides us in pretty much the same way. Now, it's maybe obvious if I move my exponential graph vertically, it moved the asymptote. If I move my transformation now of the logarithm horizontally, it's going to move the asymptote. So let's look at a couple examples of transformations with these graphs. First, we've got a function graphed out here, and we need to draw the function 3f of x minus 1 plus 2. So let's go ahead and perform this stretch. Then we'll do our translations here. So the stretch we're doing here is going to be by a factor of 3. So this point here isn't going to change. This is kind of, let's kind of take this point. We'll draw it again here just for now. Okay, my pen's doing that thing. All right, this point's going to go by 3. Okay, this point's going to, well, let's go with this one. This point's going to be 6 now. Okay, and that's probably enough to start with for our work here. Then it's going to translate. So we did our stretch. Now let's do our translation. -1, that means x minus h. So it's going to be positive 1. So 1 to the right. So this point is going to become here. This point is going to become here. That point is going to become there and there. So let's write in our sort of our translated points we've got now. And then we want to go to up. So that's going to go to here. 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 Okay. And now we can do a nice little sketch. And the other thing that I could include in this is the fact that since I know I'm moving to the right one, my asymptote I know is going to have to be right here. So I'm going to draw that asymptote first, And then I'm going to just go through the points that I labeled. And I'm not super worried about my x-intercept on this case, because I'm just drawing a nice sketch. And I know this really nice point that's our normal x-intercept translated so that it's off our x-axis. So I'm not going to worry too much about, am I actually going to nail exactly on that line? Because that's no longer quite a point of interest, right? How about this one? Let's take a peek, see at our translation. Well, we actually don't know, is it a translation or some other sort of transformation? So going from f to g of x, the first thing I notice is that our asymptote, or rather our approach to our asymptote has flipped. So it used to be going down and now it's going up. And one thing you should notice, like I'm drawing these arrows, the graph program that I'm using artificially kind of ends these. They don't just stop here. They keep going down as they go. It's just so close at this point, you can't see the difference on the graph. So it's like, I'm not going to do it. So I know there's a vertical reflection. So let's write that down. I know there's a vertical reflection. And that's pretty obvious because it's flipped. What else can we see here? Well, this point, like I said, isn't really real. But I know that my asymptote has sort of translated. So I know there's some sort of translation. So let's look at some other points first to see if there's more to it than just a translation. And so whenever I'm looking at this, I'm going to find 2 points on my function. That 0, 1 point's really strong and the 1, 2 point's really strong, or sorry, 2, 1 point. So that's 1, 0, 2, 1 is what I should have said. And let's see if there's kind of this pair of points right beside each other again on the other graph. So I'm going to follow my curve along and say, oh, well, here's one of them. And here's another. Awesome. Okay, so I did find them. That's good. And so if I'm just reflecting this, well, that point would stay the same. This point would end up down here because it's a vertical reflection. So our kind of proportions are the same. That means there's no stretch. And we can move on to how do we translate this. So I know this is kind of our back point and this is our front point. So I'm going to make this match up with this. So what do I have to do to do that? I have to go 1, 2 to the left. So our h is equal to -2 because I want to go a horizontal translation to the left. And then I'm going to go up 1. So k is equal to 1 because it's a vertical translation up 1. Cool. And they actually didn't even ask me to write a formula on this. So I've already said what I need. It's a vertical reflection. There's no stretch. And we're translating 2 to the left, 1 up. So that was fun. But let's get into some numbers here. And this is going to be pretty crunchy. And some of us will think, yay, finally, I don't have to do the flippy dippy stuff with the graphs. I can actually do math in a math class, imagine. And you know what? You're kind of right. Finally, we get to do some math. Much of this you can do with a calculator, but I'm going to request / highly recommend, hint, hint, nudge, nudge, that you do as much of this as you can by hand. So the first ones, we'll talk about how I can enter this in on a calculator, just so that we know how to do that. And then afterwards, we're going to talk about how we can do them by hand. So our first one here is log of 1,000. And if it doesn't have a base written, our sort of implicit base is base 10. And your calculator is based in base 10 for logarithms. And so it automatically, if you use the log button, it's on the left side, right by the 7 key if you're using a TI. If you just hit log, it's like, yo, okay, log, obviously log 10, right? That's pretty basic. And so it'll say this if you type it in. So all we got to do is type in log and then 10 and then hit answer. And that'll give us the answer to this. And so if you type that in, try it out, you should get 3. And that kind of makes sense, right? If we have 10 to the power of something equals 1,000, well, it's got to equal 3, right? Now, hold on. I've got a log button, but I don't have a log 3 button, log base 3. How do I do that? Not every single one of your calculators will actually have the ability to do this. So we're going to teach you another trick later on. But for now, because I'm only just showing you how to calculate, I don't need you to actually do any calculating other than by hand. if you have a TI 83 plus, I think is when they added this. Otherwise, it might be a TI 84. And if you have anything TI 84 or higher, then this will be here. What you can do is you can hit the math button and then hit alpha and then hit math. And it'll produce a log like this where it says, okay, log of, you can put something in here and you can put something in here. And so I can actually type that in. I put a 3 in there, an 81 in here, and I should get an answer 4. And that makes sense because 3 to the power of something had to equal 81. And we know, well, 81 is the 4th power of 3. Okay, next up is ln. And on your calculators, your ln button should be right below our logarithm button. So we can just hit ln and then 42. And it will sometimes open brackets for you. Sometimes it'll just say like, okay, ln, whatever. Sets of brackets around your arguments are never a bad idea, but you don't necessarily need to do them. Anyways, if I do ln of 42, I should get 3.74-ish. And you'll find that, okay, well, ln is base e to the power of something equals 42. I don't even know what e is. So obviously there's not going to be a pretty number. And e, in fact, is an irrational number. So yeah, there's not going to be a pretty number in this. When we're dealing with things that aren't a perfect match, you know you're going to get something that's going to just spit out a screwy number. You should expect decimals. So don't freak out if you see decimals when you're doing something with a ln function or a log function, especially ln. You'll very rarely see something nice with ln. Okay, let's try this one. So I'm going to hit math alpha math to get my log that I can enter in the base. My base is 4, and then over here I'm going to just have 1 over 65. Okay, so 4, 1 divided by 65. And what I should end up with is negative 3.01. Let's round it to. And that goes on and on and on as well, because I know, well, of course, this has to be a negative and it's got to be an irrational. Okay, neato, spaghetto. Now let's do some work where we actually have to think. I hate it. Actually, I love it. In my opinion, this is one of the most interesting things we do in the whole curriculum because you actually get to do some crunchy numbers by hands. You're not a slave to your calculator. You don't have to say like, oh, how does it? I know, you get to do it. So I love that. I'll also say this. I do this for a living. And so I know the powers of different numbers pretty well, not just because I'm a dork, but because it's my job. And so if you can look at this number, 256, and say, well, 4 to the power of something equals 256, and say, well, duh, Mr. Herman, 256 is the 4th power of 4, so it has to equal to 4, then good for you. However, if you can't do that, what you should recognize is, well, if they're giving this to me in a no calculator part, 256 has to be 4 to the power of something, right? And I know that, well, it's 4 times 1, or 1 4 is 4, 2 4s is 16, 3 4s is 64. If you just keep going and multiplying, go, you'll run into 256 no matter what. And sometimes you can make some pretty educated guesses as well. Okay, how about this? 1/2 to the power of something, and we'll call it x, is equal to 32 if I write this in logarithmic form into exponential form. So what does x have to equal? Well, what do I know about this? This is a reciprocal. I can see that there's sort of one's in the denominator, one's in the numerator. So to think of like flipping that, I would need a negative sign. And then I can just compare this. 32 must be a power of 2. Yeah, it is. It's 2 to the power of 5. This one looks awful. Lon E, or like Lonnie McDonald. Haha, Calgary Flames joke. Thank you, everyone. But it's actually not that bad if you consider that ln E is just log E of E. So let's draw this out. If I got log E of E, that means I'm saying, well, E to the power of something equals E. Well, if I want something to equal itself, I'm just going to say our value here has to equal 1. So let's go through a couple more of these. Okay, log 5 of 125. Well, there's that negative because it's reciprocal. And then 125 is the 3rd power of 5. Okay, cool. Ooh, this one's neat because we've got two different logs. So let's handle them one at a time. 16 in base 2, well, 2 times 2 times 2, well, that's 4. 2 to the power of 4 gives us 16. 8 is the third power. And if we add these together, then it's 7. How about this one? Okay, 2 to the power of something is 128. So I would say this is kind of a tricky one. I might do this one in my calculator, but because I practice this a lot, I know it's 7. Hey, wait a second. Notice this and this. What do you notice about the similarity between these two statements? Because they're both in base 2, and they happen to give the same answer. I bet we'll come back to that. Here's a nifty one. So just to make sure we know what we're writing, this is 2 log 2 of 64. If it's in an exponent, I can think about like solving this first. Well, our exponent log 2 is 64 is, well, that's 2 to the power of something is 64. So that's 2 to the power of 6. So this becomes 2 to the 6. Well, 2 to the 6, we just finished saying that's 64. A really cool thing, if I've got like a to the log a of b, that's actually going to just be equal to b. Nifty. Now, in this case, I don't have the same base for my exponent in the logarithm as exponent, so I should solve it out. This is ending up as 3 to the power of 3, because 4 to the power of 3 is 64, and 3 to the power of 3 is 27. Woohoo! Let's go back to this pink set of circles here, because that's really something important. The idea here is that there's a relationship, just like in our powers laws for exponents. If I had x to the power of a times x to the power of b equaling, x to the a plus b, this sort of law, if I'm dealing kind of just with the inverse of exponents, we would expect that kind of plays back for us. And we're right. It has a law that's very similar. So when we deal with logarithms, there's a bunch of different laws that we'll run into. The first is the log product rule. And here's what it states. It states that if I ever have a log of a product, so let's say we've got an arbitrary base m, and I've got a times b, it's going to equal to log of the same base a, oops, that's a bracket, plus log of that base b. Whoa, that's spicy. Let's prove that. All right, log of 32, log base 2 of 32, of course, is 5. So that's a big deal. How about this? 16, well, that's 4, and this is 1. So if we add them together, that's 5. And 16 times 2 is 32. So that matches up. 4 times 4 is 16 times 2 is still 32. Let's see if this adds up. Well, log base 2 of 4 is 2, and that's 2, and that's 1. So that gives us 5. Nice. 2 multiplied by itself 5 times, that's 2 to the power of 5, which is 32. And this is 1 plus 1 plus 1 plus 1 plus 1. Yay, it equals 5. Look at that. Isn't that a really cool relationship? And you should already be thinking, well, hold horses or whatever other animals that are rushing around. If I've got this law for products, and it matches pretty much exactly with my law for products with exponents, maybe I have one for quotients too. And you'd be right. There's also a log quotient law. And remember our log power, or our quotient of powers law states that if we've got x to the power of a over x to the power of b, it equals x to the power of a minus b. So this one's probably not that surprising. It's written at the bottom of the page, but already here. If I've got log base m of a over b, I can do sort of the logical difference of finding the difference. Log ma minus log mb. I don't know why I draw the second one in capital letters, but whatever. So let's see. Log 2 of 4 is 2. That makes sense. How about this then? What if we have log 2 of 16? Oh, that's 4. Minus log base 2 of 4, that's 2. And that's 2. Hey, and 16 divided by 4 is 4, right? So if we just did that 16 divided by 4, like we're doing here, we'll end up with that 2 as well. Whoa, dude, right? Interesting. 16 divided by 2 is 8, divided by 2 again is 4. Okay, how about this one? 4 divided by 1 is 4, so this should equal 2 again. Let's make sure it does. If I do log 2, log base 2 of 4, we know that's 2. What about this? We haven't actually run into this yet. 2 to the power of something equals 1. Well, hopefully you remember your zero power law, which says that if our outcome here is 1, if our argument or our end product is 1, then the power must be 0. And 2 minus 0 is 2. Gorgeous. So here we go. Here's our log quotient rule. Nice. The next thing that we're going to look at is the log power rule. So we knew that there's, a power of a power. We could say that x to the power of a to the power of b is equal to xab. Something very similar happens here. I don't know why this is down below. It should be like whoop up here. Either way, if I've got this law here, what I want to do is think about how that relationship happens. Well, let's take a peek at this. If I've got a power in a log, so let's say I have log 2 of, I don't know, let's say of 32, so 2 to the power of 5. Okay, log 2, 2 to the power of 5. Another way I can think about that is like this, log 2 of 2 times 2 times 2 times 2 times 2. And this, I know I can break down then into like log 2 of 2 plus log 2 of 2 plus, and so on and so forth. And so I end up with 5 log base 2 of 2's. So I can actually just bring this exponent into a coefficient at the front. So here's our actual law. If I've got log base m of a to the power of b, that's actually going to equal to b times log base m of a. Spicy. Now, I haven't deserted you mere mortals with TI-83s who are saying, I still don't know how to put in an exponent or a log with a different base. Like, what the heck? There's a really cool rule. And here's the rule down below. I should scroll down. If I've got log base b of a, I can write it as log base m of a divided by log base m of b. What? That's kind of confusing, but I'll prove it to you. Before I do, though, let's think about this fact that how can I actually use this to my help? So if you got a TI-84 and you got that question from above, like log 3 of 81, okay, I don't have a log 3 button. So what I can type in is the log 10, or because you just have the one log button, just log of our argument divided by the log of our base. So log 81 divided by log 3. And once again, you will find your answer to be 10. Not 10, 4. How does that work? What the heck? I kind of feels like I'm just cheating, right? Well, I'm not, and I'll prove it. So if I got log BA, let's say that equals some quantity x. If I want to rewrite this in exponential form, what we're saying then is b to the power of x is equal to a. Okay, great, I guess. I just made x more complicated, and I don't know. But here's a really nifty thing we can do in algebra, and that's perform operations that are the same on both sides. And we talked about logarithms as something we're doing. It's an operation. So here's a nifty idea. Why don't I go log base m on this side, and I'll go log base m on this side. So I'm applying the same operation to both. And it makes sense, right? If b to the power of x equals a, then the log m of b to the power of x should also equal the log m of a. And that's true. What can I do now? Well, clever little trick here. What if I take this x and I say, well, our log power law states that I can just make this my coefficient. So I've got x log m b equals log MA. And then all I got to do now is divide both sides by log BM. So I've got log MA over log, and not BM, sorry, MB. And that's your proof. Wow. That's nifty. So remember, we said like that equals that. Oh, transitive property. Beautiful, gorgeous, gorgeous, gorgeous. So let's make sure we got them all written down somewhere. Okay, we've done that. There's your page. Here's a couple other rules. This one we kind of talked over a little bit. Log to the power or log base b of 1. It doesn't matter what your base is. If your argument is 1, your value is always 0. If our base and our argument are equal, your value should be 1. And then we actually ran into this one as well. If we've got b to the power of log bk, then our outcome is k. I don't know why k is the letter we use. I actually just stole this from a website, but that's a cool little rule. Neat. Your goal working through this is going to be taking all these different rules, all these cool ideas, and just mishmashing, don't mismatch, mishmashing the hell out of them to get through more or less like these logic puzzles of logarithms. Is it easy? No, it makes your brain work really hard, but that's the fun of it. So what I recommend, if you're working through these, try as many of these practice questions as you can, and be ready to look at something and run into walls and have to try different strategies, have to try again, have to try a third time. But once you get a flow for how these rules can be played around with, once I understand how can I take something opaque and apply rules to it to get an answer, it's very, very satisfying. Also, it's on your diploma, so I don't care if you like it or not. You have to do it to ace the test. Anyways, there's your video. Bye.